Okay, the reason I did this presentation is that the feeling I have in the area of reconstruction, it's almost working, is that we are lacking a part. We are lacking the mathematical part. And the reason for that is that in MRI, we are mostly an engineer area. If you look at the people working in MRI, we have a lot of biomedical engineer, we have some electrical engineer, a few informatic engineer, and a few physicists. And we have no mathematician. The reason for that is that in that field, you are judged for what you do, not for what you say. And mathematicians write a lot of mathematical formulae, they speak a lot, they are exact, but they are not able to implement things and they are not able to show images. And in that field, an engineer who builds a bad reconstruction is still preferred to a mathematician who makes no reconstruction. And that has been working until now. But if we want to go further in reconstruction, now we need mathematics. And in order to convince you about that, I will try in the first part of the presentation to show you nice images. Okay, so that's when you do a reconstruction, you start with a gridded recon. You need a start reconstruction before you begin an iterative reconstruction where you build a list of images that converge. This is a coil image. That's the formula. That's all the reconstructions shown here are ferrum occipital acquisition with the Piccini 3D radial sequence. So that's all 3D radial. So you do an inverse gridding of the radial data. Here the data are Y. It will always be the letter Y. So you grid from the non-uniform, where is the mouse? To the uniform grid, then you do an inverse discrete Fourier transform. This is the deapodization that cancel the effect of the convolution because the gridding is a discrete convolution. And these are the factors to have the right order of magnitude. And you get a coil image that looks like this. And if you want to combine the channels, the coils, you need to estimate the coil sensitivity. Here is the example of the real part of a coil sensitivity of the imaginary part. And in order to reconstruct, to combine the coil, you solve this problem. So it's the sum over all the channels. So the index Y run over the channels I. And this problem, the coil sensitivity is just the stack, the C, the matrix C, it's a block matrix. It's the stack of all coil sensitivity, where each C here is a diagonal matrix that contains all the element, all the value of the image. You take the coil sensitivity, you list all the values in a vector, you put them along the trajectory, and you get your C1, C2, and so on. And to solve this problem, you just have to compute the pseudo-inverse. That's just a few lines of code in MATLAB, okay? And then you inverse every channel, you do the gridded recon for every channel, and you multiply with the pseudo-inverse of the coil sensitivity that we can summarize like this, and you get an image like that. That is this image is nicely sampled because it was all the bins, the respiratory bins were combined here with the technique of Chris FNAV, and then the gridded recon was done. And that's two different examples of a gridded recon. The right is the GPU NUFT, which has no normalization of the gridding weight, and the left is a NUFT we implemented in Lausanne, which is a bit different. We normalize the gridding weight to have a better gridding. The interesting thing about the two is that if you take the half number of lines, that's just an image of the GIF. If you take the half number of lines, you see the image to the right is beginning to get worse. You take the half and you take the half. So the less line you have, if you don't normalize the gridding weight, the worse it gets. While on the NUFT we implemented, you still have an image that looks like a heart. So that would be a better start image to start with, for example, the left image. Once you have a gridded recon, the next simplest recon to do is sense. And I regret I don't have, I only have this simulated data set. It's because I prepared some data on the cluster in Lausanne, and on Friday, the cluster stopped working because they did some maintenance. So I compute this 2D radial example in the train. This is 4 different implementation of sense. The better one, you see that better converge is the one right down. That's the conjugate gradient. The first is a gradient descent. You see the residuum here. The second is a variant of the gradient descent. The third one is it's three-step gradient descent, and then you begin a new gradient descent. Three-step of conjugate gradient descent. Then you begin a new conjugate gradient descent, and the better one that converges faster is the conjugate gradient descent. That's the standard algorithm to solve this square of linear map problem. So if you are not happy, if you want a better image than that, for example, to register, to find the motion field between adjacent frames, you probably need something like this. For example, that's a static reconstruction. It's a reconstruction of one frame where you regularize spatially. So you penalize the variation between adjacent pixels in the image. So you see here the 80, it's a GIF that represents the 80 frames of each iteration, and you see how it converges. And this image, on purpose, the regularization is very strong here because I wanted to show the effect of spatial regularization, so it blurs everything. But this image can be very useful. It's not to underestimate, because with such an image, then you can find the motion field very easily because it has low noise. You see the broad structure, and once you have the motion field, you can start a new recon to improve the image. That is from Ludovica. We first did a Simba recon on each frame. Then we found the motion field between adjacent frames. So the motion field here that you see in blue is the one that maps this image on that one. And once you have these motion fields, you can do a new recon that look like that. That's the data fidelity term. And that's the term that penalizes the difference between two adjacent images. So you deform this image and you subtract this image. They should be the same in principle if the deformation is correct. And we use it as regularization. Okay, that's not my slide. It's a slide of Ludovica that explains what we do. So we use Simba, you extract the cluster, you do some gridded recon. Maybe you should ask her to have a better detailed explanation. And what you get is something like this. I hope you see the difference. So there is much less noise on the second reconstruction that is regularized with motion fields. The image down, the bottom images, with respect to the upper images that are gridded recons. And that's an example on pediatric pressure. And another way to reconstruct, that is the most advanced way that I programmed it until now, is to do a first reconstruction where we regularize in time by penalizing the difference of adjacent frame, but without motion field, because before you do any reconstruction, we don't have the motion field, and we get pretty decent images that we use then to find the motion field. Here is the witness image that show how the image is converging and the residuum. And then once you have the motion field, you do a second recon, or you add the motion field here in the regularization, and you get an even better image. And if you want, that's the witness image for this reconstruction that show a few images of every 10 iteration, I think. That's the residuum, and you see on the bottom graph is the the sum of the difference between adjacent forms, so the temporal total variation. That is the comparison between without motion field and with motion field. And if you want to see the difference, I selected some picture. The recon including motion field is on the right. And well, you can see the difference. It speaks from itself. The contour are better delineated. You see less noise. We have a kind of weird noise in the floor artifact, but that's another discussion. The more shocking images I found is here. You see, when you don't correct with the motion field, this wall here disappear. When you add the motion field to the recon, it will appear. So, and this part of the muscle here is sharper. Right. So that's example of images that we can get if we regularize with motion field. And I think that the first time in Lausanne that we can add the motion field into the reconstruction framework. Okay, that was just some example. How much time do I have? Okay, it's not bad. Do I have 20 minutes more? Okay. That was example to show that if we do the things mathematically correct, we can reach our goal, and we can improve the images by adding motion fields. But the way to go there, and that's my part, that's the first message I would like to say today, is to understand the things exactly. And I think my feeling, speaking to people at ISMRM, the people in the field, is that it's an engineer field, and the things are done approximately. We don't do the things quantitatively correct. And I think one of the reasons is that all the reconstruction until before compressed sensing, it was only FFTs, right? You do a Cartesian acquisition, you do an FFT recon, and you have your recon. That's how the FFT, the discrete Fourier transform, is working. The forward is just you shift your data, you apply the FFT algorithm, and you shift it back. Backward is the same. You just have a different matrix for the FFT. And if you want the right scaling, you just have to multiply with the voxel volume. For the inverse, you have to divide with voxel volume. For the conjugate transpose of the forward, you divide by the volume of a cell in the K-space times the inverse discrete Fourier transform, and the adjoint operator is the same like the inverse. And the three last operators, if you neglect the factor here, and it's what we do mostly in engineering, we neglect the factors, it's always the inverse discrete Fourier transform. And because there were no difference, the engineer called it the backward. So when you speak to engineer, you ask them about the Fourier transform, they will tell you the forward and the backward. And that's probably because everything that is working when you do Cartesian. And as you will see, when you do non-Cartesian, these three notions here, the inverse, the conjugate transpose, and the adjoint, are different. They are not equal anymore. But the engineer continued to speak of forward and backward, and they introduced some errors into the code because of that. And what I would like to do today in the rest of the presentation is to show you a formal description of sense, because sense is the start of any iterative recon. Compressed sensing, which is now a family of very different recon, start all from sense. Sense is the mother reconstruction, and you first have to understand that and to describe the inner space, the inner product space correctly and the adjoint correctly if you want to implement all this recon correctly. Before I start with the math, I just show you an example to show that the inverse is not the adjoint. That's an image, and that's a deformation field I invented. And if you deform this image with that deformation field, you get that. and if you apply the inverse operator, you come back to something similar. You see, there is a difference. If I plot the two images, the inverse is a bit different from the original one because there is some rounding errors, but you still get something that is close to an inverse. That's the difference image, to show that the inverse not exactly the start image. Now, if I start from the transform image and that I apply the adjoint, I get that, which looks pretty artistic, but it's not the same. So you see that the three have the same form. It looks like an inverse, but it's clearly not the same. And I like this example because it shows that mathematically the adjoint operator is totally different from the inverse, but engineers still call them backward, and they mix everything, and that the things are going wrong. Okay, so let's start with the formal description. I'll show you these slides, which are very abstract, and then I will try to explain the content of this slide. So you have two vector spaces, X and Y. X will be the image space, and Y will be the data space, so the list of numbers that we measure in the scanner. So every vector X in the X space is a list of pixel values, it's a vector, and every Y in the Y space is a list of values, which is the FID we measure. And we have a map from the image space to the data space. The map is the model. You give an image, and it returns you the data that models this image. So in our case, in the case of sense, the A is the coil sensitivity times the NUFT. This is the image of the map. It's if you take the entire X space, you map it in Y, you obtain the subspace of Y that goes through 0. Here, the black dots are the origin of the spaces. And this is the null space or the kernel of A. That's the subspace of X that is sent on 0. That means all the vectors on the dotted line are sent on 0. And you have an adjoint map. So to define the adjoint, you need some inner products in each space. I will define what it is. But this defines the notion of orthogonality. The inner product defines the notion of orthogonality and adjoint map. The adjoint map is a backward. So it goes from Y to X. And as for the map A, a dagger, this sign is called dagger, it has an image that goes with the origin. And you can show that the image of A, which is called the co-image, or it has a name, I don't remember, it's orthogonal to the kernel of A. The image of a dagger is orthogonal to the kernel of A. You can show it easily. And the null space of the adjoint is orthogonal to the image of A. And this has a very important implication, is that I will show, that's the conclusion of my presentation, is that when you compute the gradient of the objective of sense, the objective of sense is the delta fidelity term. If you compute the gradient of that, you obtain a vector that is in the image of our adjoint, which is perpendicular to the null space of A. And so what we do in sense is that we have a measure point Y in the data space, and we want to find an X that is saying the closest as possible to Y. And there is a theorem in linear algebra saying that if you have a point in a space and you have a closed convex space, like a linear space, there is only one point in that convex space that is the closest to Y. So in other words, we have to find the X that is sent on the K, which is the closest point in IMA to Y. So we have to find an H, so that A of H is K. But H is actually any element in the preimage of K. If you take the set theoretical inverse of A, you get a subspace in the X space that is parallel to the null space. And that is the set of solution of sense. If you take any value in that subspace here, minus 1 of K, you will be sent on K. So any point here is the closest to Y. So any point in that space is a solution of sense. And you can travel if you add any vector, if you have an edge here, and you add any contribution that is parallel to the null space, Let's write it. You take A of H with any vector in the null space. A is linear. A of H say times n, but n is in the null space. So we still get A of H, which is equal to K. Okay. So you can travel in that subspace here. You will still have you will still land on the K. So what we do when we do an iterative sense reconstruction is that we start from an images called x0 here, and then you find the gradient at the point x, which is, as I said, is the image of our adjoint, which is perpendicular to the kernel, and you travel in that subspace until you reach an edge in the solution space. So that is what sense is doing. It's an orthogonal projection of your start value onto the solution space, which is parallel to the null space of your NUFT. And if you do a conjugate gradient descent, of a gradient descent is exactly the same. You just modify the search direction that you stay in the image of adjoint. So you stay in this subspace. So, and now what I would like to do for the rest of the presentation is to define what is in this picture. That's about one word about regularization. The purpose of regularizing is to extend the possible K to a broader range, because we may admit that the data are not optimal and that we may find a better image in the neighborhood of the solution space that is better. And the purpose of regularizing is to find in this blue set here, to find a solution that is the best among the other. So that means that the data fidelity term allows to travel in that direction, and the regularization allows to travel in that direction parallel to the null space to find the preferred solution. Okay, so the X space is Cm, which we will admit to be isomorph to R2M. Well, I arrived to the end. That's the beginning of the presentation. Okay, so M is the number of voxels, but we will describe the things in terms of real space. So the same for the data. Here I describe the situation for one channel, but if you have many channels, it's exactly the same. You just have to replicate the blocks. But I didn't do that for the presentation because graphically it would have been not readable. Any complex X, which is a real plus the imaginary number times the imaginary part, we want to read it as a real vector. You just stack in a column the real and imaginary part. And the same for a map from Cm to Cn, which is a real part plus an imaginary part. You rewrite it like this as a block matrix, which is a map from R2M to R2N. And you can show that this is just a representation of that. It's the same. There is an isomorphism, and this map here is an isomorphism. You can show it like this. If you multiply A, the complex A with the complex X, you get that. So RA times Rx minus IA Rx and so on. And if you multiply the block matrix, the real representation of A times the real vector, you get the first component that is exactly the real part, and the second component that is exactly the imaginary part. So that means that this diagram commutes, and that means that everything that is complex can be described in terms of real vector and matrices. One word about the conjugate transpose. You take the minus imaginary part and you transpose the two matrices. In terms of real block matrix, it looks like that, but it's exactly the transpose of A. Okay, so the conjugate transpose for us will be exactly equal to the transpose of the block matrix. So I just say that to say that we can describe everything in terms of real space and it's working. We don't need complex number. Even the Fourier transform, you can write it like this and you can describe both the mathematics in terms of real spaces. And whenever I have a function on that's in any position on a value, you can discretize it on a set of position, and I will write f as the list of values sampled in the position Ri. Okay, that is this f is the discrete approximation of the function f from the position Ri. Okay, so now if I have a function that it is the raw data function. Oh my god. It takes any position in k-space as argument and send it on a complex value. It's what the measurement process is doing. Okay. If you compute the squared norm of that function, by definition is equal to that integral, and you discretize it to approximate it with your discrete samples. Okay, you get this discrete sum where the volume elements here are actually the volume around each of your points in your trajectory. Okay, so you can then rewrite it like this, and you see that you can rewrite it as a matrix Sy times two real vectors. That's very important. That's the key to understand the mathematical structure. Where the Ry is just the list of volume elements of your trajectory. We call it data compensation in our field, but it's really volume elements actually. Okay, so that the square norm of your raw data function can be approximated with this scalar product. Okay, so we have an inner product or scalar product on the space Y. That's every pair Y1, Y2 on a real value by the mean of this expression. And at this point, and that's a very important point, it's not the same like the Hermitian form that you form with the complex Y, complex conjugate, Sy and Y2. This is called the Hermitian product. And if you develop it, you see that the real part, only the real part is exactly equal to our scalar product. If you take the real part of the Hermitian product, you get that. And that is our scalar product. And it appeared, speaking with the engineer, they asked me in my implementation, why do I take the real part of the Hermitian product in the conjugate gradient descent? It is because the real part is our scalar product. And that's another source of error in the implementations, is that engineers don't think about that. And that's a problem, because your scalar product needs to be real. In the conjugate gradient descent, you do a line search, you do an exact line search, and this line search is given by your scalar product. If it returns a complex value, it's not a line search. It does not work. So that's why it's important to understand this structure. So you do the same, exactly the same on the image space. You have the image function that you can discretize on the pixel center, and the square of the square norm of the function can be discretized like this. And here, the volume elements is just the volume elements of your voxel, which are all the same. So the Rn are equal to the same voxel volume. That means we have an inner product on the space of images that sends each pair exponents to a real value, where this time the matrix of the scalar product is S6, which is equal to the voxel volume. And finally, we have a map from the image space to the Y space, which is the cold sensitivity composed with the NUFT. Okay, that's the cold sensitivity map. The NUFT is just a replication of the NUFT for each channel, and it has an adjoint. By definition, you can show that there is exactly one map, so that this is equal to this. I try to go faster, and that is really the key. If you want to retain only one thing of the presentation, it is this equation here. So the adjoint is the matrix of the scalar product in Y space times the transpose matrix of A times the scalar product matrix minus 1. Okay, and what we do usually in our field is that we admit that Sx and Sy are the identity, because we don't take the density compensation to the scalar product into account, and that's a source of errors. So the adjoint is not the transpose, it's not the conjugate transpose, and it's not the inverse. It's really the adjoint that is defined by this formula. So when you want to solve sense, which is finding the minimum of that function, you have to take into account in your norm that we speak here of the norm in the y space that include the Sy. So when you compute the gradient, you can show that this Sy appear here. You can modify it by adding a 1 here, which is the voxel volume. And if you write it like Sx minus 1, you see the adjoint appearing here. And putting this scalar here in front of the parenthesis, you see that the adjoint map, the gradient is the adjoint map times something. That means that the gradient of the data fidelity term is in the image of the adjoint. So it's what I wanted to say. And that's why, if I go back to the description, that's why when you do sense, you start with a value and you always travel in a space that is the image of the adjoint to reach a solution. So you can show it, but it's intuitively clear from here that the solution of sense is the projection of your start value onto the solution space.